Hi, everyone. We'll be starting shortly.
Hello.
Hi there. Can you hear me fine?
Perfectly.
We'll be starting in about 5 minutes. I'm just going to just post a couple more advertisements and then we can kick things off. Okay, then let's get things underway. Um, Welcome to the Flower LLM AMA. It's great to see everyone here. Um, we are going to run this in a slightly unconventional AMA style, and that is if you want to ask your questions, please post them in the Flower LLM channel that's on the Flower Slack. If you look at the slide that I'm sharing right now, you'll see how to join if you currently haven't joined. Um, we can also take questions from um, this YouTube live stream. And so, yeah, feel free to ask us questions. We have a number of the contributors here with me right now. And yeah, really, we're happy to take any and all kinds of questions about the paper, about the motivations. And it's such a rich topic that I'm sure there's a lot of sort of tangential areas that we can also explore. Um, we have also collected a lot of questions from folks since launching the paper and the result back in sometime in March, early this year. And moving forward, we've given presentations at different venues. We've recently revised the work um, with this new result where we're able to train up to 3 billion parameters. And so from that experience, um, there have been a number of questions come in. We've also had questions in the Slack before. So we're going to go over those questions too, but we're going to also um, prioritize those questions that come in live. So here we are. Um, I am first going to just quickly set the scene slightly um, by sharing the paper directly so we can see what we're talking about. So let me just stop sharing this slide. And I'm going to try something very dangerous and try to make sure I share the right tab of the right browser with the paper in it. And I think I've done this correctly. Yeah, looks like I have. And then this is just to remind everyone what we're talking about. And so we recently, we being the CamOSys Cambridge Machine Learning Systems Lab, along with Flower, um, did this piece of research where we built an experimental system called Photon that runs on top of the Flower open source framework to perform federated learning in the context of pre-training large language models. And this work, as I mentioned, was first announced March 14th. We released an archive paper around May with a lot of the details, and then we revised it very recently to describe this transition from 1.3 billion being the maximum size that we had demonstrated experimentally to 3 billion, along with many other factors. And so if I just scroll down here, again, just setting the scene, it describes the purpose of this work is sort of really manyfold. But one way to describe what it tries to do is demonstrate the technical feasibility of leveraging GPUs distributed around the world and data that's siloed at these locations where compute exists, um, allowing us to combine these things together, even though they're connected with very poor, slow, wide area links, and yet still able to train um, these massive LLM models. And one reason, quite a strong motivation to do this, is that it allows strong resource sharing. So whereas right now there are these races existing within certain organizations to accumulate GPUs together that are logically connected by high-speed data center style links, this would enable many parties to combine their resources perhaps together or to leverage their resources within a single organization that might be physically separated in order to train what is currently one of the main, I don't know, boundary frontiers of AI. And so if I just scroll down this paper a little further, I want to get down, don't want to get you too dizzy, but show you that there's a system here. Let me just page down a system here called Photon. And so one of the distinguishing characteristics is that this is a real system. It's live in the sense you can stand it up and combine it with real GPUs around the world and actually start to train these models. So that's enough of a background, I think. I can stop sharing carefully. Yes. And then you'll see everyone here that's joined us today. I think we can just go around. People could just say maybe they're like a one-liner as to what they're most excited by about this paper, very briefly. So just name and what's your most excited thing that you're really into, and then after that you could hand over to the next person while we kind of get to prime these things up. So I'll name a person. That person can do their thing. They can hand it to the next person, and we can efficiently go through. So I'm going to start with Jan Gao. I've known him for quite a number of years. So over to Jan. What's the thing that excites you the most about this piece of work that we've been doing?
All right. I think the most exciting part of this paper is we really make the federated LLM pre-training come true. So that means we can make use of the protected data that is not available in the public data set. So yeah, that's will be a big step for I think for LLM training. Yeah.
Cool. Who are you going to hand over to?
Uh, how about Lorenzo?
Cool.
Sure. Yeah. Can you hear me well?
Yes.
Cool. I'm a PhD student here in Next Group, main author of this paper. I'm mostly excited about the several research directions that this paper can open, and the very cool things that we will be doing in the next months or a couple of years, thanks to this work. So yeah, this is what excites me the most. I will hand it over to Alex.
Hello there, I'm Alex. I'm also a PhD student. I'm most excited about getting access to more data to train on, and also about potentially combining very different data sources into the optimization procedure, because it's very relevant to our ability to scale these models into the future. And I'm going to hand it to Bill.
Hi there, I'm Bill. I'm also a PhD student in the lab. What excites me most about this work is really the opportunity to democratize large language model training and tap into compute and tap into data all across the world to put this into the hands of more organizations and more people. So I'll pass the baton to Tom.
A PhD student also here in Camel's lab. And it's really hard to cherry pick one exciting thing about the paper, but if I have to do one, then it's perhaps the observation that the bigger the model is, the better the convergence is. So if you look at the perplexity charts in the paper, it's this fascinating story of the four plots where the bigger the model is, the better the curves are looking. So that's very exciting.
Great. Well, let's start off with a question. One question that underpins this work, at least partially, is are we going to run out of data? And so I've heard some people think we are. Certainly, if you're in that camp of we are running out of data, then this might be one means by which you can overcome that. So this is not exactly a precise question. It's a bit loose, but are we running out of data, and how does this relate to FlowerLLM and the photon system would be the question. Who would like to take this?
Yeah.
Okay, so essentially, I'm of the opinion that we'll run out of naturally produced or human-produced data. And even if we do not consider the term running out in its strictest meaning, it's still we were still in a problematic period for acquiring data easily, in the sense that we're in this self-fulfilling prophecy where we create models that then heavily impact the sort of data either people produce or what's available on the internet, which creates an Ouroboros situation, right? The models end up consuming data that other models have produced. And from an information theoretic perspective, this just means that you're trying to extract meaning from nothing. Now, in terms of like actual estimates, we have reasonable guesstimates from several papers about this. But essentially, over the course of the next few years, up until 2026 or 2030, we would expect, based on known laws regarding the speed of how quickly the internet scales or how quickly humans produce text, we would expect us to not run out of human-produced text. And even if you combine all the modalities possible, the current exponential growth pattern of LLMs cannot continue without getting access to non-publicly available data.
Yeah.
That's about it. Yeah, that's about it.
Well, there's certainly excitement about synthetic data, and I think it will have its place. I wonder if synthetic data might be most promising, whereby you're seeding that synthetic data from real data, perhaps from a federated source, so you can maintain the privacy, but the data so that's synthetic is has information in it. But at least here, I think wherever this goes, I think the need to be able to access large amounts of data and continuously access it, irrespective of what new regulations might come along or what sensibilities we start to introduce, is going to be important. Yeah, good one, Alex. I guess another part of this work is federated learning is often associated with small models. So a lot of the federated learning work that's occurred, some of the success stories include the Google keyboard model. It's a great use case, very compelling, delivers a lot of value, both in terms of utility to millions around the world, and yet still protects their privacy. So really, is a one killer use case of federated learning. And I suppose the world has still struggled to find dozens of these things. We've found singular numbers and isolated buckets. But one thing that's common across these examples that one could point to is that they tend to be relatively small models. And then in the world of machine learning, the frontier of what people are working on has gotten bigger and bigger. And so in some sense, there was a time not so long ago that it would be reasonable for someone to ask if the relevance of federated learning was diminishing from that lens, from that perspective. So I guess an interesting question would be, what does FlowerLLM and the photon system and the models that it's able to train say about this aspect, about the ability of federated learning to scale, its applicability and utility to large models, and things of that nature? Again, sorry for these long-winded questions, but who wants to speak to this one?
I can reply to this one.
Yeah.
Well, what I think for an Elspeth is that we always tried to make Photon in a way that can enable collaboration whenever the resources available are for clients. Of course, this doesn't tell us much about all possible future applications of this thing, but at least they tell us that any institution organization participating in a federated learning with just a few GPUs of a data center level, but not only data center level, they can all participate and collaborate, even though they don't have, a huge data center full of H100s, which is a common setup for training an LLM in the centralized way. So we think that Photon allows this type of collaborations, even for compute poor actors, it's like good pool participant. Whether this will be enabled at laptops or smartphone level, still, I think, a question. Laptops may likely work to some extent. There's plenty of research works trying to fit this type of pipelines into smaller devices like laptops. So yeah, I'm sure the future will say more about this.
Great. I mean, just to put a bow on it, I'd also say that it just is it's an empirical demonstration that federated learning can scale model size and data volume much larger than anyone would have guessed not that long ago. And so there's a lot of skeptics, I think. I talked to a lot of people in the world of federated learning. I talked to a lot of people about adoption and what prevents them adopting federated learning to understand, where the cracks are, where the seams in the current NML landscape, and see how FL and related methods can help. And something that is often said is that there's skepticism about how well it'll scale, and moreover, what is the exact quality of those models? They might say to me, oh, yes, I suppose if you put enough effort into it, if you lean in really hard, anything's possible. Okay, so perhaps you can train in this approach. But then what is the quality of that model? And then it seems from these initial results that models of very large size can be trained using federated learning. And moreover, if we look at the figures in this paper, they show that the model is comparable. There's no signs of it being worse than the centralized one, although we need to do further digging, and these are just early results. But there are no signs of that to this point. We have some other questions, some live questions. So let me go through these one by one. We have our first question here comes from YouTube Live. It's from Bajali. I'm sorry for the pronunciation of names. He says, I've previously worked on aggregation algorithms in FL. I've used Flower, but I haven't read your work on FlowerLLM yet. He says, I was working on the FL in healthcare sector. I'm called Fed Health, and the data is huge. And so here it needs larger GPUs to process the training. Oh, I see. And then he's saying, so I plan to do a final project of this in this way. And he wants, I guess he's trying to say if FlowerLLM is going to help. So I guess that, yeah. So let me just try to summarize this really interesting question, which is for a person working in Fed Health, the data is really huge. What could FlowerLLM offer them? Perhaps maybe in the long term. Bill, do you want to sort of take this one? So someone's working in FL Health. What potential holds for FlowerLLM and someone working in that domain?
This sounds to me like more of a Lorenzo or Alex question. Can I pass the baton to one of them?
Absolutely.
Sure, there's no problem. Well, my opinion with FL in the medical setting is that it's a very promising technique for taking advantage of all the medical data that is available, and we cannot really use easily, I would say. I have a lot of friends working with hospitals and medical data, and they struggle a lot every time whenever they have to play with the data, train machine learning models, and all these sort of things. There are a lot of regulations. These are for us, right? Like these regulations are built, as Bill may tell us better, they are built for us, like for protect the people in the first place. But for practitioners, people want to use this data for training and for, giving the community more powerful tools, maybe for medicine and sort of things. It's very difficult to comply with these regulations. So federated learning has this amazing property of not moving the data from where it's collected. And this helps a lot in complying with the regulations. It makes things easier to some extent, but also more complex because it's difficult to train a machine learning model when you can't see the data distribution, right? FlowerLLM can help, of course it can. Photon is a system that can run on hardware available to hospitals, for example. So if, for example, there's a setting in which some number of hospitals want to collaborate and put together their language data for, I don't know, developing some Q&A tool or chatbot or these sort of things, they can certainly build their system on top of Photon to do this. And this is very, very, very promising for them because they couldn't use these amounts of data otherwise.
When it comes to the sort of privacy thing, there's always an aspect of regulation and essentially how it maps onto what we know we can do in machine learning. For example, even though we don't move the data, there's a question on whether we should potentially apply differential privacy or general privacy enhancing techniques, which are directly supported by any federated system. And because federated learning gives you this very nice encapsulation of this is an entity with because privacy is important by itself. So let's say hospital, you can devise your algorithms in such a manner that you can get decent guarantees based on the requirements of the participants, which would be much more difficult to do if you needed to, let's say, pull all the data together and then make sure that it's encrypted, or let's say anonymize it or something like that. So I think you can definitely use the standard federated learning techniques in order to make this amenable to very private situations.
Yeah, good answer. Makes sense to me. Let's we've got plenty of questions coming in, so this is quite exciting. Let me see. So next question, I think in order was, I think from Michael. Michael has a question about privacy, and he is asking a question related to our experiments in particular. And so Michael's question is, how did you preserve privacy in your experiments? How did you approach the issue of the privacy accuracy trade-off? And I think we might start with Alex, as he has done a companion piece of work that speaks to this issue more directly. And then we can unwind a little bit and go back to this original paper, the one I showed at the start of the session, and discuss what's going on with that paper in terms of privacy. So Alex, do you want to speak about, you have this technique, it's called FlowerLLM, and it fits on top of the Photon system. And how does it cope with this privacy issue? And what are the challenges in doing this too in general?
First, we need to clarify the setting a bit. Privacy in the context of this sort of works is a bit different than in a, let's say, cross-device situation, right? So if we were training these things directly on user phones, that is very much a matter of personal privacy, which may have much harsher implications upon what techniques and what algorithms you need to use. In this context, both Photon and my work are mostly centered around cross-silo situations where the participants are organizations, which may be collaborating because they don't have enough resources, they don't have enough data, or because of, let's say, legal or regulatory concerns or something along those lines. So in this context, their privacy is more along the lines of, let's say, either concerns regarding data leaking to a model that maybe crosses boundaries, which they maybe hold data that you're not supposed to allow to pass a boundary. For example, if you're training a model partly in the US and partly in Europe, Europe is going to have more stringent requirements upon your way of processing data from users. And for example, you may not want to extract too much information from the European user base, otherwise may end up in trouble like Meta currently just did. So in the context of this situation, my work argues that by having sort of hierarchical decomposition of a standard federated network, you can more easily enforce these sorts of concerns by restricting your purview, as in if you have a specific situation which require privacy guarantees, you can restrict down a particular branch of a hierarchical structure like the tree and make sure that you are applying that technique there. This is the easiest to see when it comes to something like encryption. So let's say you have a secure aggregation protocol whose purpose is to hide who participated in the aggregation procedure. Then you can do this in the region where this is necessary and completely skew this additional computational cost if you don't need to do that. In terms of the major work that we did with Photon, we were primarily concerned about not having to move data and thus allowing, let's say, copyright holders to not have to directly share everything that they have. For example, you may be some kind of book publisher or something else, and you just have your own data and don't want anyone else to touch it. That's where I would be going with this. Do you have anything else to add, Lawrence?
I think you described it very, very well. Yeah, to be specific, we didn't apply any other privacy mask technique in the main Photon paper. It's certainly something we are interested in doing in the future. So yeah, we'll see how it goes. But it's still, I think, an open research question, especially for pre-training in large language models.
Yeah, I think it's important to acknowledge what we've done, what we haven't done. And so we deliberately designed the work we've done so far to be based on federated learning principles with the aim that in time we can show examples that need privacy to be attended to in a way that can be. Because federated learning is basically an opportunity to build a private system. And then you have to decide whether it's needed for the application that you care about. And then you have to decide to what degree you want to do this. What are the attacks that you worry about? Therefore, what are the techniques that you want to bring to bear? And so in this first paper, because it's pretty much the first time people have shown you can do pre-training at all with federated learning, we basically had to really dig in deep to get the system to work. And we felt fortunate that federated learning was still able to be done. And therefore, all the other pieces of work, of which there are numerous pieces of work that build on top of federated learning using various types of techniques, differential privacy, and the list just goes on, are available to us. It's just that in the first paper, we were unable to use them. In Alex's paper here, was able to use them and specifically use differential privacy, but there's a long way to go in this. And yeah, so it's a good question, but it's basically still, even in, I guess it's also important to say that the use of these privacy preservation methods, even in centralized settings, is still very much a work in progress as well. Yeah. Okay, well, let's move on through these questions. There's one from Bahajali again, but I just want to drop down and come back to him. I'm going to ask this question, and it says, hi, do you plan to explore the idea of building a speech FLLM that can process speech in discrete units and generate speech? So speech FLLM at some point. So I guess, so if I understand the question correctly, this person, Captain Fryo, is asking, can we build, do we have intentions to build a system that would synthesize speech? Because he says, can process speech, discrete units, and generate speech. So that sounds like a speech synthesis system. And I know that Jan has actually spent quite a lot of time building FL systems with respect to speech. And so while I guess I would say as a precursor to this answer that we don't have, we haven't specifically identified certain application domains we want to go after. And I think we are going to be largely guided by finding organizations that want to partner with us to give us access to private kinds of data, private or other kinds of data that's perhaps difficult to onboard during the pre-training process. Maybe it's a lot of data. Perhaps it's locked in a network that's difficult to integrate into these kind of data centers for doing pre-training in a conventional way. We want to basically find real examples of the type of data that this method would allow you to leverage, and then and design a system that's agnostic to task. So meaning that we'll find that data, work with people to find real concrete forms, and build models based on that data. And so the tasks that we solve will be informed by that data. But I feel your question touches upon just FL and speech in general. And so maybe Jan, do you want to tell us more about where speech in FL sits right now and any limitations that you could kind of see if we want to scale it upwards? Anything along those lines?
Well, to be honest, I'm not quite very familiar with the speech LLM thing, but I think it's a good direction to go. And as you mentioned, if the next step we found like a private data is speech data is it's a good way, good direction to go. Yeah, why not? We can try to like link to the speech domain. And I think not only for speech, maybe probably the multi-modality would be also the future direction, because and the multimodality is in the world is everywhere, and it's very important to make use of how to make use of and combine with the existing LLM is also a good like direction. Just in my
Makes sense.
Yeah.
Oh no, yeah. Well, we're in the land of very fertile research territory. So basically all we have is opinions informed by the work we've done. So it's good stuff. And Maida, I think I'll come back to you with this other question because it's quite related. And the question is, could you share some insights from working with federated LLMs? And I guess you could also just consider foundation models just generally that you think could be useful for other modalities like image, video, or voice. So could you share some insights from working with federated LLMs that you think could be useful for other modalities like image, video, or music? Or maybe I throw it up to everyone if it's a bit of an open question. So I guess what did we learn from the work we've done so far that would have relevance for how we might do large scale training on other modalities like image and video and music? I could kick us off by saying that one thing we've learned is that it is possible to train the model architectures in an agnostic way. So our methods are not tied to any particular architecture. So we could use the same approaches and thinking we've done on this particular transformer standard kind of conventional approach to training an LLM, but we could swap that out. We could put in some multimodal model quite comfortably. Also, the training process is fairly generic. As we move forward, we might start thinking about more exotic things. But right now, you could train almost any network. We wouldn't be sure how well it would work, but it's possible.
I can chime in here.
Yeah.
Yeah, I'm really excited about federated learning for video models. I think what is often true and the catalyst or motivator for doing this for text is maybe even more true for video. You have often large file sizes that are going to make the transmission of these videos into a central server pretty difficult. And you also, in the video space, if you think of the large video data sets that are out there, there's the public ones like YouTube, but a lot of the good private video data sets out there, they're going to have a lot of security. They're going to have intellectual property issues around them that are going to prevent folks from potentially wanting to send those into a central server as well. So I think it's a really exciting frontier to start to think about how we apply this all to video.
It's true. I guess also this method might allow us to maintain more clear awareness of where data is coming from. Whereas if you're perhaps downloading data or scraping it from the web or various kind of sources, if you're not too sure where that data has actually come from, instead, if you have sort of active participation through organizations or individuals opting in under this federated style of training, then you have much better methods and opportunities to understand where the data came from.
That's well said. Yeah, I think training data lineage is probably going to be even more important than video, and federated learning can be a way to achieve that, right?
Totally. Yeah, let's bang through these questions. I see, here's a good one. And this one, Tom, I'm going to go to you with this question. This is from user Black Yogurt, and he or she says, my thesis is about reducing communication overhead in FL. Do you know of good resources in this domain? And they have not been able to find good code or papers related to this subject, especially compression methods. So Tom, maybe do you want to speak to I could speak to anything in this area. It's often the case, depending on how many resources you have available in an FL system, that communication can be a squeeze. It particularly obviously is going to be stretched under these pre-training of LLMs. But this individual was also asking for any good resources, papers perhaps, or other things, other thoughts on managing communication overhead in FL.
When we started training these large models with federated learning, much like you said earlier, Nick, it kind of uncovered one thing where, historically federated learning has been used for applications with very small models or reasonably small models. This time really the communication is becoming an issue, so much so that we looked into it, and we have now a work happening in the lab where we're actually doing some major refactoring of the Flowers communication stack, which will allow all sorts of new exciting scenarios. In terms of both academic applications and the practical software, I would recommend the person to just wait a little bit, and then there will be stuff released by us in the near future on this topic. And so specifically, there are many ways how you can optimize these things. For example, at the moment, if you just want to use the straightforward techniques, in Flower you'll be limited to 2 gigabytes per message, and then some of the larger models might not even fit into those messages. So an improvement is coming very shortly to the main branch of the framework, which will enable these scenarios directly. But then there is so much more you can do as well. Maybe to give a little sneak peek of what's coming, so you can enable these scenarios where you can have one-to-many network communications rather than, let's say, propagating a new version of a central model to each client individually. You can do it at once, so the branching is happening on the network level rather than you having to send these things in repetition. And then you can be also very smart about retransmitting previously seen data. So that's something also which are looking at the moment. So there is a possibility to optimize things where you can choose not to transfer certain parts of the model which were previously transferred, let's say in previous training rounds. I know this sounds maybe a little secretive, but there's work coming. So I will just say watch this space, and yeah, we're working on it already.
Great, good answer. I would say that there are some pretty interesting works out there already that have been done to optimize the communication overhead. One of the ones that jumps to mind is a piece of work that we did in the lab not that long ago, that the name of which I'm forgetting. Can someone help remind me of the piece of work?
Works. There was one from Shinji called Zero Pel that just the communication costs.
Yes.
Basically, also the researcher from Italy doing some follow-up work related to sparse training and for reducing communication costs. I'm not sure if the code is publicly available, though. I may need to double check. But there's plenty of resources out there, mainly public code repositories to start from. I think the good part of our photon system, but in general, Flower, is that you can highly customize the way you store the parameter into this message that you then exchange. So, for example, in the case of sparsification, what one can do is just take the most important weights, keep them, and what are least important, just remove them, and then compress even lossily in a lossless way, and then exchange a message that is much smaller in size. So the communication is going to be quicker if the network is low, or just is going to be much simpler, because FL runs on heterogeneous networks that are usually not super friendly to large payloads or continuous streamings, for example.
Right. It's zero. Oh, yes. Sorry, Alex, you go.
I have two things to mention here. One is it's not just the communication that matters, it's the ratio of time spent communicating versus computing. In the case of our large language models, communication is very heavy, but it is highly infrequent. So if you can do a lot of local training, you're alleviating a lot of the problems already. The second bit is FL is likely to be resilient to many compression methods, simply because the aggregation procedures are already very noisy. You are aggregating a bunch of models that may have found different local minima. You're already kicking them out of the local minima. Even lossy compression may be fun. And there's a bunch of works on compressing machine learning models, either in a manner that minimizes the loss of accuracy, which can be applied naturally when you send a payload. And then you are going to have smaller payloads, and your aggregation procedure is going to probably not harm you that badly, essentially. Those were the two things I wanted to mention.
Yeah, no, excellent. Makes sense. Yeah, thank you, Lorenzo, for reminding me. Zero FL is the paper I was thinking of. And it does a nice job also of being able to balance the compute and communication overheads, largely just using sparsity. People can find that there was iClear a few years ago. Let's see, another question here is you mentioned in the paper that you have, this is a quote, that have at least a few data center level GPUs. So I guess this is a stated, occasionally stated requirement or expectation of clients at this stage. So the quote is, have at least a few data center level GPUs. And then the question is, I want to ask whether NVIDIA RTX 4090 can satisfy this requirement, or maybe the NVIDIA A100 GPU. So it's a question. Yeah, so feel free, anyone wants to jump in on that one.
I think I can give an answer to this. In short, what we did was with GPUs that were slightly more capable than the RTX that this person is mentioning. But of course, we don't need to use A100s or H100s or these sort of things. Of course, VRAM memory is very important, but in the future, I'm sure that we will find a way of training even on smaller devices like RTX 4090s. As far as I'm concerned, I think some of the models that we have actually trained can run on that type of GPU. So potentially a client using one of them could participate. Yeah. But of course, yeah, we are well aware that VRAM amount of memory available is usually a problem if you want to train a large language model. I felt that despite this allows you allows you to train maybe even smaller chunks of the same model. And there's been work in the research community regarding some training procedures that were a little bit different compared to ours, using maybe some structures like mixture of experts or these sort of things. And of course, when you split the architecture in several parts, this is more likely to fit the smaller GPUs like this one that was mentioned.
I think that the main limitation is just memory, and that currently, if you had a number of cards in the client or node, where the sum of the GPU memory was sufficient to hold the model you're trying to train, then with a bit of massaging, our approach could work. Even though we haven't tried the sort of cross GPU on one client or node situation. But I guess the main reason why we talk about data center level GPUs is just to distinguish this against a federated device centric sort of series of thinkings that actually require that bring to bear a lot of assumptions that are different from cross silo. Right.
Can I add something a little bit to this answer as well, please? So
yes, please do.
So generally, if you compare those two classes of cards, so let's say on one hand you have the data center level GPUs like A100 or H100, and then you have, let's say, the RTX series cards. And if you look at the performance per dollar ratio, right, you'll realize that the RTX series and such like are much better deal in terms of performance per dollar. Now, the reason why NVIDIA can charge so high prices for these cards is that these cards, like the latest RTX series, they don't have NVLink, right? So you can't create these short distance, high bandwidth interconnections with these cards. And so that's what you need for the centralized training. Now with federated learning, what you can do, and Alex talked about the ratio between computation versus communication a few minutes ago. So an interesting observation here is that you don't need those high speed interconnections, right? So you can have your federated learning clients computing in isolation, and so you don't need those data center grade GPUs to perform that computation, which is a very exciting opportunity, even from the cost perspective.
Cool, great, yeah, absolutely, I completely agree. Makes sense. Let's look. There's a question here. The question is, any plans to try encryption for private inference? And so I think the question here is getting at there might be a interest in encrypting the resulting LLM so that then you could do inference on that LLM while the model weights are encrypted. So I think we would have general interest. I'm not familiar with the current state of being able to do inference over encrypted models, generally speaking. But popular methods like homomorphic encryption wouldn't be able to scale up to a model of this size at all. So it's really a non-starter unless there is work done. And then I believe there are methods that you can take out small chunks of a model and run small parts of the model within things like trusted hardware or variations thereof. But I don't. Does anyone here have knowledge about how one might go about this, or any thoughts on the matter? I think it's in play for us. We're interested, of course, but I get a sense no. But that's cool. I mean, it's a reasonable question. So I guess the short answer is it's at least to the limits of my knowledge, I think it's not possible or is very, very difficult. But I'm really not up to date. And it's somewhat orthogonal to what our research aims have been up to this point. But we understand the kind of issues because the issues would be that if you're really concerned about some of this input data, well, then there might be a good reason for you want to encrypt that model, either at deployment, or perhaps you're even thinking about during training if the model is moving around. I mean, there are methods to handle that issue that we could talk about, but they are really on the edge of what's possible too. Okay, let's move forward, I think. We've done as much as we could with this question, I think. Okay, question is, can you throw some light on how federated learning can be applied on small imbalanced data sets? So I get a feeling that this is perhaps a little bit separate from the work that we're talking about here, but I'm happy for us to answer this question. Obviously, because we would like to talk about federated learning. I don't know if anyone, I don't know, Jan, do you want to talk about how you might do that? This question is quite vanilla in some sense. It's like, how would you do federated learning when the data set is small and the data set is imbalanced?
Yeah, I think so in this case, if the data set is imbalanced, so as far as I know, usually people use AUC as the training target instead of the law. Maybe it's combined with entropy loss, but you know AUC is a good indicator instead of the accuracy to in the imbalanced data sets. So this technique could be used in the federated training, I think.
Yeah, makes sense. It's also logical to start from a pre-trained model that's related to the domain that you're interested in as a way to kind of overcome this small amount of data that you have. There's actually a lot of thought in this space. If anyone else wants to chip in, feel free. I guess I've got a question here that came up out of ICML last week. Someone approached us and said, FlowerLLM, oh, looks pretty interesting. How does the EU AI Act relate to this work? What are your thoughts on this? And I'm going to throw this to Bill because he might have some thoughts about how this work relates to the EU AI Act and things of that nature.
Definitely. Thank you, Nick. So I think it's okay to see the EU AI Act as an implicit endorsement of federated learning. It does not explicitly require federated learning, that's for sure. But a couple provisions in the EU AI Act may, lean people in the direction of federated learning. I'll just mention briefly what those are. Article 15 has some explicit security provisions for AI systems, keeping your data and your model secure. The EU AI Act also explicitly coexists with GDPR and its data privacy protections. So I think overall, the EU AI Act is going to be a boon for federated learning. I think it's going to nudge a lot more folks in that direction. And of course, this work is all about making this possible for some of the most exciting models out there today, large language models. I will say, something that we've talked a lot about, and we have at least one paper in this space, and maybe more coming. With this kind of nudge towards federated learning that the EU AI Act arguably provides, there's also some new complications. So one that we talk about in a paper that was at a workshop at ICML, the Gen Law workshop, and this is a collaboration with TUM and with IBM. There are certain data governance provisions and data quality provisions in the EU AI Act. And we all need to work together to figure out how that works in federated learning where we don't have direct access to the data. So we may not be able, at least at first glance, to say much about how it was governed or its quality. So we need to work through that as a research community. And then another issue that is raised, and I think circles us back towards this other work that we talked about earlier, which is the World LLM, is what if we have folks in the EU who may be adopting certain privacy or security protocols based on what the EU AI Act does say about privacy or security, and they want to be in a federation and federally train a model with folks who don't exist under the same privacy or security regulations, and may, as a result, have a different security or privacy protocol that they've adopted, different privacy enhancing technologies that they're adopting to comply with those policies or with those laws. How can we get them together in the same umbrella federation of federations? So that's really what one of the pain points that World LM is focused on, right? So yeah, there's a lot of interesting conversations to be had about the EU AI Act and how it relates to all this work. And I think there's also a bit of a call to action for the research community to figure out how we really make federated learning work in the wake of this regulation, but also the others that are likely to come about in the next couple of years.
Yeah, okay, I completely agree. I think it's going to be an interesting catalyst for work in the space. So what I'm going to do now is I'm going to mention 3 questions, and then we can go through them one by one, and that might be helpful. And so one question is that people want to know that actually, this is a sort of a synthesis of questions that have come in quite a few times. They would like to know, so you're training models that very few people on the planet have ever done, seeing empirical results that are seldom have been seen. Tom actually mentioned one of the observations earlier that was interesting, but they're interested in, can you give me a couple of things you've seen that you want like to describe to people? They're interested in knowing what have you seen empirically that is interesting. So that's one question. So that's one. Question 2 is we know LLMs memorize data. You're using FL, and so you're kind of implicitly wanting to make that private. What can we do about that issue? And then question 3 is there is a need for insight for processing images, such as medical images, like human organs and things like that. But I'm just trying to unpack this question. But I guess the question is are there FL papers that can help inform this problem? So I guess the problem is dealing with medical images. So those 3 questions. Happy to see people answer any one of those 3. And they could, I guess, as you answer that, you could briefly restate the question because it's slightly difficult.
I can dive in quickly on the middle question, which is about memorization, LLM memorization as regards to federated. Yeah, so we know this exists outside federated learning. I think as a first step, there's work to be done just understanding what it looks like for federated learning. So I know we do have some work in our lab that's about the problem space and trying to document exactly whether this is happening and exactly what it looks like. I think that's a preamble to the solution space and figuring out then how we mitigate it. So that's how I would respond to that question, is pretty much just watch this space and maybe as a first step, let's try to document the problem as regards federated learning specifically.
I guess I just jump in on there. It's an interesting challenge. I think as your answer somewhat brought up, this is an issue. LLM memorization is an issue with LLMs. And so it's sort of orthogonal to FL. Like you'll see it happen with centralized, you'll see it happen in any circumstance. Yeah. And so solutions probably that exist outside of how do you train it, whether FL or centralized, will be applicable to these models. And so we probably would end up using some of these solutions that inhibit memorization. That being said, we have done some empirical work that was used in a course we did with deep learning AI. This was done by Preslav, Jan was involved, and other folks. And while that wasn't done to a sort of scientific level of rigor, it was basically showing recipes on how you can dial up and down the type of utility of that model and therefore related memorization as you would measure through common attacks. And it showed that federated learning tended to reduce that level of memorization. But that was in the context of federated fine-tuning compared to centralized fine-tuning. And so I guess we would hope that this type of issue can be better controlled under federated situations, but we will have to look into this. But there are some signs that federated models are a bit more resistant to this factor, potentially. Alex has something to weigh in on this question, I believe, or a different one.
On memorization.
Yes.
There is also a related question of can you separate where the model stores information versus where it learns how to think, right? So in the case of an LLM, the obvious situation would be, is it memorizing facts or is it learning how to interpret a specific sentence and how to construct it and deconstruct it, essentially? And in the case of federated learning, there may be ways to attempt to, let's say, aggregate on the ability to reason without necessarily aggregating on the information that is memorized. But this is a hard problem. Separating where machine learning models store information is very difficult, and it's unsolved right now. Another thing is federated learning gives you access to some kind of discrete space of places where you could have memorized data from, which gives you a bit more of an advantage. So if any group of people ever request you to forget their data, so let's say you have a hospital in your federation, or let's say you have a country that now requires you to forget their data, you know what information came from them, you may have a bit more debug. That's about it.
Yeah, okay, cool. Does anyone want to answer that first question, even if it was briefly? Like, what are one or two things that have been learned?
I think I can answer this one. I think another good observation for the one that made earlier is related to those experiments in which clients were highly heterogeneous. I think that we clearly noticed, and we kind of expected it, but not to this extent, because the different velocities at which they locally converge before pushing the pseudogradient up to the server. So this was something that we're kind of used to some extent. Heterogeneous client, they train differently, they have different losses, they propose different pseudogradient to the server, and then the server tries to merge them together. But we were a little bit surprised by the different velocities then. We were following completely different patterns, as if they were speaking two different languages.
That's cool. I mean, I think there's dozens of these observations that have come out as we kind of go over the kind of empirical results. All these, we've got the checkpoints, we have all these different sort of artifacts that come out of the training to sort of look over. I was quite interested to see this early signs of the models being easier to converge under this FL regime as they got bigger, which is useful because as things get bigger, the opportunity to tune parameters diminishes. So the less sensitive they are, that would be a great useful property. Yeah, and so I guess we can answer this last one, and then we'll start to wind down. So I guess so that was about insights for medical image processing, like human organs and patient details, and implementing it with FL. So there was a reference guide of your paper. I have an answer, but I'm happy to yield other people who want to provide an answer. I'll be brief on this one. It's a pretty this question is interesting. It's kind of a little wide. It's kind of sort of a wide sort of question, and I would point to a piece of work that is being done at Maryland. I can find the link while we're answering another question, but essentially it's a group at Maryland, and they've been using FL to build models that do segmentation tasks and other tasks of that nature by joining together repositories from different health providers, hospitals. And it's been nice work. They presented at CVPR, and I think there's a domain-specific workshop for which they received, I believe, the best paper. And I'll post it in the Slack channel for FlowerLLM for those who are interested. But that's how I would approach this. I'm seeing we're a little bit over time, and so I guess I'd just start to wrap this up. But I'd give the chance to anybody who wants to just make one final comment or thought about the work. Feel free to jump in there, and then we can wind things down. Does anyone want to say a passing final thought? Could be something they want to, maybe perhaps the answer to a question that was never answered, that they really felt there was a kind of essential question that they wish someone had answered. No? Okay, that's cool. Well, thanks for joining us, everyone. I will make sure I post that paper from Maryland for the person who asked this question, Chiragmin. And we can always run this again. We'll look into seeing what people would like to do, what works for them, and we'll consider what would be most valuable to folks. Thanks for joining us. Thank you for all these questions, and thank you for everyone who dialed in, who worked on this paper. So there's Bill, Jan, Alex, Lorenzo, and Tom. And yeah, thank you, and enjoy your weekend. Take care.
Thank you, Nick. See you later.